In this section, we will introduce the Poisson distribution and look at how it can be used to calculate probabilities. Consider a situation in which the number of cars that pass college is recorded and an average is found to be 1 car every 15 seconds. We want to use this to calculate how many cars would pass the college in 10 minutes. Now consider why this would not be a binomial distribution and why this situation is similar to a binomial distribution. So the main reason this is not a binomial distribution is that it does not have a set number of trials. The question, how many cars could pass the college in 10 minutes, in theory could have no upper limit. However, in reality, there would be a maximum number of cars that could pass in 10 minutes. However, theoretically, there is no upper limit. The situation is similar to the binomial distribution because the outcomes are discrete. They all take integer values in this case, the number of cars passing college. The outcomes are also independent of each other and are random events. A discrete random variable x can be said to follow a Poisson distribution in a given interval, where lambda is the average rate that event can occur in that time period. It's written using this notation, so this means that x is modelled with a Poisson distribution with a rate of lambda. In order for the discrete random variable to follow a Poisson distribution, it must satisfy these conditions. There would only be a whole number of outcomes in the given interval. The outcomes of the event would occur at a constant average rate throughout that period. The outcomes of the event should be independent of each other and occur at random. The outcomes also occur one at a time. For each of the following situations, consider whether you think that the random variable described in the situation could be a Poisson distribution. So first of all, the number of customers that come into a shop in a random minute during a 24-hour day. This would probably not be a Poisson distribution because it is unlikely that there will be a constant rate of customers over a full 24-hour period. It's likely that there will be some periods that were more busy than others. Also, the shop may well close during the night. Next, the number of calls to a help desk between 1 p.m. and 2 p.m, given that it is known that the average number of calls during this period is 22 calls per hour. This is likely to follow a Poisson distribution, and it will be described as x is modelled with a Poisson distribution with a rate of 22. This is assuming that the calls can't be put in a queue. So if the calls are put in a queue, this would count as two events occurring at the same time, which is not allowed under the Poisson distribution. Next, the number of daisies in a randomly selected square chosen from a large area of parkland. This is unlikely to qualify as a Poisson distribution because if it is a large area of parkland, it is likely that there is not a constant rate of daisies. For example, there may be different types of soil or different sun exposure, which would cause the number of daisies to vary considerably across the area. Next, assuming that people turn up to a party at a rate of 7 people every 10 minutes, if we wanted to work out the probability of 5 people turning up in a random 10 minutes, would this qualify as a Poisson distribution? The answer is no. This is because party guests tend not to be independent of each other. People will often arrive in groups, so there would not be a constant rate. If it's known that there are on average 3 imperfections in a metre of metal bar, if we wanted to calculate the probability, that in a randomly selected meter of metal bar there will be no imperfections, would this qualify as a Poisson distribution? The answer is yes, and we could model this as X is modelled as a Poisson distribution with a rate of 3. Supposing it's known that a train on the same route goes through a station at a rate of 4 times per hour, if we wanted to know the probability that a train passes at least 3 times in the next hour, could we use a Poisson distribution for this? The answer is no. This is because it's likely that the trains are running every 15 minutes, so are not random events. This formula can be used to calculate probabilities of an event happening a certain number of times in a given time interval. If X is modelled using a Poisson distribution where the rate, the average rate of the event occurring in that time period is lambda, then Px equals X means the probability of the event occurring exactly X times in that time period, and it can be calculated using this formula. E to the power minus lambda multiplied by lambda to the X over X factorial. We're going to use this formula to complete the table. So we're given that X has a Poisson distribution with a rate of 1.5, and we're going to calculate the probability of the event occurring 1, 0, 1, 2, 3, and so on times in that time period. So substituting X equals 0 into the formula and lambda equals 1.5, we get 0.223. If we substitute X equals 1 and lambda is 1.5, we get 0.335 as the probability. For X equals 2, we get 0.251. And then for X equals 3, 4, 5, and 6. You can see that by the time we get to 6, the probability is very low. This is because if the average number of times the event occurs is about 1.5, the probability of it happening 6 times in the same time period is very small. If we plot this as a bar chart, we can see the distribution. The distribution does continue for values of X greater than 6, however they will be very small, tending towards 0. We want to find the expected value and the variance of X for this distribution. Using the expected value formula, which we know is the sum of each of the X values multiplied by its probability, we get an expected value here of 1.5. This is not a coincidence, this is the same as the rate in the distribution. We can then calculate the variance using the variance formula. Again, we have the expected value of X squared, squaring each of the X values and multiplying by the probability, minus the expected value of X all squared. This again comes out as 1.5. So that the expected value of X and the variance of X are both lambda in a Poisson distribution. This result is true for all Poisson distributions. To summarise what we've covered so far, if X follows a Poisson distribution with a rate of lambda, then we can calculate the probability of X being a particular value using this formula. The mean of the distribution will be lambda. The variance will also be lambda. And because the standard deviation is the square root of the variance, we can say the standard deviation is square root of lambda. Pause the slide now and calculate the following probabilities. Use the formula to answer these questions. So for question 1, we are calculating the probability that x equals 4 in a Poisson distribution with a rate of 5.5. So using the formula, we can substitute lambda equals 5.5, x equals 4. This gives us a probability of 0.156. For the probability that x is less than 3, we see that this means that x could be 0, 1 or 2. Note that x can't be negative because x needs to be the number of times that an event occurs, so it must be 0 or greater. So we could calculate the three probabilities for x equals 0, x equals 1, x equals 2, and add the three together, giving us this probability. For x is greater than 3, this means all of the x values, 4, 5, 6, 7, and so on, continuing forever. The easiest way to calculate this is to realise that this is all of the probabilities except for the case where x is 0, 1, 2 or 3. So we can calculate the probability for x is 0, 1, 2 or 3 and then subtract from 1. This will give us the probability of the remaining x values. So we calculate 1 minus the probability that x is 0, 1, 2 or 3, and this gives us 0.798. Finally, the probability that x is greater than or equal to 3 but less than 5. We can see that this is just the x values 3 or 4. So calculating these two probabilities gives us a total probability of 0.269. We can also use a calculator function to calculate these. There are two functions on the calculator which can be used to calculate probabilities for the Poisson distribution. They are both on menu 7, which is the distributions menu. The first one is the Poisson Cd function. This gives the probability of x being equal to a specific value. This does the same function as the formula that we have just been using. The second function is the Poisson Cd function. Cd stands for cumulative distribution and gives the probability of x being less than or equal to a specific value. If we wanted to find the probability that x is strictly less than a value, we would need to convert it into a problem involving x being less than or equal to a value. So for example, if we wanted to find the probability that x is less than 5, we could calculate the probability that x is less than or equal to 4. So we would use 4 in the Poisson Cd function. In general, probability that x is less than a is the same as the probability that x is less than or equal to a minus 1. Similar results, we have the probability that x is greater than a is p. If we found the probability that x is less than or equal to a, it would be 1 minus p. For example, the probability that x is greater than 5 is the same thing. If we did 1 minus p, this would give us the probability that x is less than or equal to 5. If we want the probability that x is greater than or equal to a to be p, then we know that the probability that x is less than or equal to a minus 1 to be 1 minus p. And finally, the probability that x is greater than a and less than or equal to b is p. We could calculate this by finding the probability that x is less than or equal to b minus the probability that x is less than or equal to a. These can all be verified by substituting numbers in for a and b. Suppose it is known that the bubbles in a glass of lemonade are randomly distributed, and we know that there is a rate of approximately 4 bubbles per 1 centimetre cubed. If we wanted to know the probability that in a randomly chosen centimetre cubed of lemonade there were 6 bubbles, we could do this by first of all defining this as a Poisson random variable. In this case, we would have x is modelled as a Poisson distribution with a rate of 4. This is because it is known that there are 4 bubbles in 1 centimetre cubed. We are now going to calculate the probability that x equals 6 and lambda equals 4. This can either be done using the formula or by using the Poisson Cd function on the calculator, which is quicker. So the probability of there being exactly 6 bubbles in a randomly chosen cubic centimetre is 0.104. We now want to find the probability that at least 3 bubbles occur in a randomly chosen centimetre cubed. Again, we know that x has a Poisson distribution with a rate of 4. At least 3 means x is greater than or equal to 3. In order to convert this into a less than or equal to problem, we know that this means that x cannot be 0, 1 or 2. Therefore, we can calculate 1 minus the probability x is 0, 1 or 2. This can be found using the Poisson cumulative distribution on the calculator. So we would go to the Poisson Cd section and we would substitute x equals 2 and lambda equals 4. We would then calculate 1 minus this probability to give us a probability of 0.7619. In part C, we want to find the probability that 30 bubbles would occur in a randomly chosen 2 cm by 2 cm by 2 cm cube. We can see here that the volume of lemonade has been scaled up. So the volume of the new cube would be 8 centimetres cubed. So therefore the rate will also be scaled up in the same way. So the rate is going to be scaled up to 4 times 8. So we can define the random variable now as having a Poisson distribution of 32. We can now calculate the probability that x equals 30 using lambda equals 32. We can either use the formula for this or we can use the Poisson PD button on the calculator. This comes out as a probability of 0.0681. 3 clothing stores collected data on the number of sales they made over a given time period. We want to consider which of the stores could use a Poisson distribution as a suitable model for the sales. So in store W, the sales in a 2-hour period were recorded for 10 days. In store X, the sales for the full day were recorded on 8 days. And in store Y, the sales over a 5-hour period were recorded for 12 days. First of all, we can calculate the mean and the variance for each of these sets of data. Pause the slide and calculate those now. So we find that for store W, the mean is 14.4 and the variance is 14.44. This suggests that we could use a Poisson distribution because the mean and the variance are very similar. In store X, we get a mean of 25.1 and a variance of 53.9. These are not similar, so Poisson distribution would not be a suitable model here. And in the third store, we have a mean of 58.2 and a variance of 59.6. While these are slightly further apart, they are still relatively close when we compare to the size of the numbers. So Poisson distribution is likely to be a suitable model here too. We now consider what the distribution of sales would be in stores W and Y if we were to take this over a 1-hour period. So because in store W, the sales were recorded over a 2-hour period and we came up with an approximate rate of about 14.4, we divide this by 2 to get an approximate rate for a 1-hour period. So for W, we would use a Poisson distribution of 7.2. Similarly for store Y, the sales were recorded over a 5-hour period. So for a 1-hour period, dividing by 5 gives us approximately 11.9. Suppose we were going to add together the total sales in an hour in store W and store Y, and we wanted to know what the probability that that total was 20 would be. Because the rate of sales for both stores is over the same time period, 1 hour, we can combine them together. So lambda for the combined stores would be 7.2 plus 11.9. The sum of two independent Poisson distributions also gives us a Poisson distribution, so we can add together the two rates into a single Poisson distribution. So W plus Y, the sales in store W plus the sales in store Y, would have an approximate Poisson distribution with a rate of 19.1 sales. So using this, lambda is 19.1 and x is 20, using the binomial probability distribution, we get a probability of 0.087. So to summarise, the sum of independent Poisson distributions is itself a Poisson distribution. The key word here is independent. The two distributions must not affect each other in any way. So if x has a Poisson distribution with a rate of lambda x and y has a Poisson distribution with rate lambda y, then the sum of those, x plus y, will also have a Poisson distribution with a rate of lambda x plus lambda y. If we have the two Poisson distributions that are the same, so x plus x, we can calculate this as being a Poisson distribution with a rate of 2 times lambda x. And this can be continued indefinitely for the sum of any number of Poisson distributions. This means that generally speaking, if we have multiplied x by n for some scalar value n, this can be modelled as a Poisson distribution with a rate of n times the original rate. Now complete exercise 2A on page 22.